Now, for the last part of day one of FEDIL Industry Days, we would like to put in practice what we have discussed just yet and give you the opportunity to learn more about data. Data is the backbone of the digital future. Without data, there is no digital economy, and there is no digital economy without data. We would like to give you an insight on data literacy, knowledge management, and the space sector. Therefore, we invited Dr. Loveneesh Rana, the head of Concurrent Design Facility at the University of Luxembourg. But first, I would like to invite you to discover the video describing the Conceptual Design Facility of University of Luxembourg.
Rockets and satellites inspire the kid in all of us, but designing them is complex. Let's have a look. The very first step is to develop the concepts that become technologies and systems required for space missions of the future. This involves teams of specialists from a variety of disciplines to develop a perfectly synchronized solution. This is a crucial phase, and making the wrong decision here can mean the failure of the whole program. This ideation phase influences 80% of the life cycle cost. Traditionally, the design of space systems is done sequentially. This is a time-consuming process where the exchange of information is slow and inefficient. A modern design approach instead uses simultaneous processing and integration of multidisciplinary design. This is the concurrent engineering approach. By enabling a team on a project to make decisions in real time, designs for new space systems are more accurate, delivered on shorter timelines, and costs are reduced. The recently developed Concurrent Design Facility at the University of Luxembourg, CDF-LU, is a state-of-the-art environment where concurrent engineering is practiced to design systems and technologies for future space missions. At CDF-LU, we are developing a broad portfolio of capabilities to apply them to a diverse range of applications, including satellites, rockets, and other space systems. The distinguishing feature of CDF-LU is its flexibility. The lab has a modular configuration as it adapts the capability uniquely to an individual application. The CDF-LU is an innovative platform for materializing new ideas in space system design, from technology feasibility in spacecraft design to space architecture planning. At the CDF-LU, all these elements come together to get us much closer to realizing the next big idea in space.
Chers spectateurs, nous recevons encore des commentaires par rapport à la traduction. Dans le coin droit de la vidéo que vous venez de voir, il y a une petite icône avec un casque et puis il y a écrit français pour français, il y a écrit anglais pour anglais. Dear audience, in the bottom right corner, there is a little icon with a headset. There is written English for English and French for French. You can just click on it to get the right translation. Now, I hope you enjoyed the little video on the Conceptual Design Facility of University.lu. My 10-year little brother, and as many other children, is fascinated with rockets and spaceships and spacecrafts. And he got very excited when he saw the little rover Perseverance landing on Mars 2 weeks ago. Now he wants to become an astronaut, and I tell him to have fun in learning astronomy, mathematics, engineering, and science. However, we will see that also data literacy is very important for the space sector and jobs in the space sector. Therefore, we invited Dr. Loveneesh Rana, again, head of the Concurrent Design Facility at University.lu. He will give us an overview on data literacy and explain us how it is applied in the space sector. But dear Loveneesh, thank you for being here with us today. So when we contacted you to participate in FEDIL Industry Days, we saw that you have a very impressive CV. We would like to know a little bit more about your person, where you have been and what you have done before. Thank you.
Well, first of all, thank you, Angela, for introducing the Concurrent Design Facility. Currently, I'm working in the University of Luxembourg, where I'm acting as the head of the Concurrent Design Facility and also teaching in the Interdisciplinary Space Master Program. Before here, I was in the US, where I completed my PhD in aerospace engineering. And I also worked on several projects throughout the research tenure. Now I'm leading the Concurrent design facility, where our goal is to develop the next generations of softwares and tools which can be applied in designing the spacecrafts and space missions of the future.
And why are you going to talk to us about data?
So data, as you know, is becoming an integrated part of our lives every day. In technology field, it's giving us power to look at more trends and to improve the ways in which we conduct analysis and designs of spacecrafts. There are two elements, if you can think about how the spacecraft is designed. Before it's put in practice in form of a hardware, there is a lot of work that goes on the paper, where you do a lot of calculations, where engineers are involved in finding the right balance among different subsystems to put together a system, a rocket, spacecraft, satellite, anything. So in this context, data and digital platforms give us a higher accuracy and efficiency to conduct those analyses early on. And that's why data is becoming ever integral and always more important in designing the next space missions.
Thank you very much, Loveneesh. So I guess I gave the right advice to my little brother to work in the space sector. So now we can start the presentation on data literacy. Ladies and gentlemen, Loveneesh will do now a presentation on data literacy.
Okay, so we begin with the data literacy, knowledge management, and space sector. So first of all, what is data literacy? Data literacy, the very basic and very recognized definition of data literacy is the ability to read data, to analyze data, to argue with data, and work with data. Now, this is a more standard form of data literacy definition that you will find at several places online, on Wikipedia and everywhere else. This is one of the most accepted form of data literacy. But before that, what is data? Data is, as we have a fair bit of idea, it is the factual information in forms of numbers, texts, images. But as you see in these references from Webster and Cambridge Dictionary, information is a key part in definition of data. But at the same time, there is this very well-known pyramid in computer science and data science, which puts data at the bottom, and then information comes above that, and knowledge, and then eventually wisdom. So in this sense of how data means to a computer and to computer science, it's very different from what data means to us. And I show this definition of data and knowledge that I came up with and I applied in my research, where data for me meant specific information about one particular case study or one particular type of vehicle or system, while knowledge is a more generic information that is applicable to a class of information. And this is more relevant because you have to know the context before you can start working with data. You have to know what is your purpose of dealing with data and knowledge. And that's continuing in that contextual work of how do you work with data. I define data literacy in terms of these four elements, in these four ways we interact with data. And the very first one is to be able to collect data, to find the right data, and to be able to know where data sits. Once we collect data, we have to understand what data means to us, what are the dimensions in which we are working with data. And based on that understanding, we can develop frameworks and methods and tools to be able to process that data to the needs of what we want to use it for, and eventually to be able to communicate data. So in today's digital world, the data literacy is important in being able to even communicate what you're doing with data.
Yes, so now you will tell us a little bit about your research.
Yeah. So now I'm going to talk about three research projects that I was part of, where I applied the the application of data and knowledge base. The very first one being the design of a spacecraft. This was also topic of my PhD dissertation. But before going forward, let's look at what is the general life cycle of a product. The very first step is when a customer initiates a requirements in form of a request for proposal. And answering to those requirements, a group of industry bidders apply for that RFP. This is the conceptual design phase, where the industry is designing the product on paper right now, meeting those requirements, and they apply for they respond to the request for proposal. And this is the conceptual design phase. It's also called pre-phase A, phase 0, gestation phase, or ideation phase, because here for the first time the non-tangible requirements are converted into a tangible product. And once the bidder is selected, the most efficient, the best design for the RFP is selected by the customer, the bidder, the manufacturer can start working on maturing the design through preliminary design phase, detailed design phases, providing more details, developing higher accuracy, and eventually moving on to building the prototype and converting that into a workable system that is then launched in the market. So the key phase here that I was involved in was the conceptual design phase. It's the first phase where the blueprint of a physical system is developed. And it's the phase where decisions are made which actually go through for the 80% of the life cycle and eventually account to the 80% of the life cycle cost. Here you define the shape and the form of the product, what kind of technologies would go into developing this product, and how the product would be used. And it's usually done in advanced design departments, in future project offices. ESA has a concurrent design facility in Northwick where they do this kind of studies. And that's where our CDF in University of Luxembourg is also trying to innovate with the next generation of tools and methods. And as you can see, this is a very abstract way of thinking where you don't have a physical product, but you have certain needs for it. And for the first time, you have to come up with a blueprint, and that's why you require special sets of tools. Now we are going to look into how the data and the most recently the AI has been playing a key role, and new tools are being developed. So this presents an analogy between a human decision maker and a digital decision support system. This was ideology and philosophy we pursued in my previous lab in Texas, Aerospace Vehicle Design Lab, where we compared how a decision maker, an expert decision maker, makes decision. It's based on the memory, which comprises of all the learning that you have been through, knowing the information on the factual grounds, but at the same time also balancing that with his experience. And that's where the decision makers of today are making the decisions. And on top of that, they combine that with the logical framework. For a computer, this becomes part of three domains: the data domain, the knowledge domain, and the process domain. So as you can see, the memory for a computer is the data domain. The experience of human is equivalent to a knowledge domain, and the logical bit is the parametric process. And a combination of these three elements leads to a best practice decision support system. During my PhD, I developed on designing a generic design synthesis process, or a tool that could be applied to designing space access systems or spacecrafts in general. And I applied the GDSP, as the process was called, in designing a special type of spacecrafts which were vertical takeoff, horizontal landing. So the spacecraft would take off as a rocket vertically and would land on a runway like an aircraft. Talking about GDSP a little bit, there are three top-level systems module that constituted GDSP. And they were the database, knowledge base, and parametric process. again referring to the previous slide where I was showing data, knowledge, and parametric process as the key essential elements of a decision support system. So a database for me, specifically for the VTHL type of vehicles, involved information that was specific to one particular type of vehicle, while knowledge base was a generic information. And parametric process element was synthesizing both these types of information into a mathematical framework. Now, I have to give you an analogy in terms of a car, Audi A4 becomes a database element because there is just one type of car. But a six-piston, six-cylinder engine, combustion engine, or a steering wheel becomes a more generic element that is across all the types of cars. Same way, a parametric process is actually taking both those information and synthesizing them together to make the next generation of Audi A5 and A6. So that's a simpler analogy. And how these three elements were connected were the database and knowledge base would feed into parametric process, while database would also be somehow related to knowledge base because you take multiple specific data points to make a more generic set of information and knowledge. Now, the overall study process, going back to the 4 steps, 4 aspects of data literacy, the very first step of collecting data was done through development of the database. The understanding bit came from developing a knowledge base, while the processing of data was done in the parametric processing box within the GDSP framework. And eventually, the results produced were communicated through various graphs and plots and infographics that could communicate the results better, as I'll show in the next few slides. So this slide gives an overview of one type of application in the GDSP process, where the mission was to design a space plane coming back from the International Space Station and entering the Earth's atmosphere and landing on the United States landmass on a runway. And as you can see on the left side of your screen, it shows all the types of combinations that can happen to make one type of space plane. And this is just a lifting body configuration. So this is a configuration of the space plane that does not have any wings. Similarly, there can be a wing body configuration and a blended body. And this plot at the end shows the results where I was able to design 636 design concepts and measure them against each other. So this is a bigger picture information where I could synthesize a lot of information and eventually present in a manner that could be applied by a decision maker to take the next decisions going ahead in the design cycle.
Thank you very much, Loveneesh. Looking at this slide and looking at this matrix, I see many dots. And could you explain us a little bit further how can we find in this matrix the most optimum solution for a future product? And further, since there are so many dots, is it possible to use all of these possibilities to develop a product afterwards?
Sure. Yeah. So as you see here, this one matrix contains 636 design concepts. So just to design one concept, I had to develop a system which would make use of 200 plus variables. And after I was able to design all of them, I had to put them together and measure them on certain performance criteria. And as you see in the corner where I identify the most optimum solution, that includes the minimum weight, the minimum performance, cost performance metric, and the maximum volumetric efficiency. So these are 3 criteria. Now, all of them cannot be developed into the product. There might be some which might not fit into the feasible corridor. But the idea with this kind of analysis is to find the best starting point, and then you can move ahead and develop that starting point further. this is something that usually is skipped out or is not released in the public domain whenever a proprietary space company is doing the conceptual design phase. So in this manner, this kind of studies can help to go ahead and start from a most optimum point rather than going from the previous generation of products.
Thank you very much. This is also replying to the question of what is the benefit of this conceptual design method compared with other methods where you maybe use what exists already in the research to work from there on. I think you have also a second use case for us.
Sure.
Exactly.
Yeah. So the second use case is regarding the knowledge management and how we can use the data and data existing to define the knowledge for the future generations. And this was also a part of the research that I was doing in my PhD, where I studied the space plane's history from the last 60, 70 years, as you can see here, starting from 1933, where the first space plane concept was initiated, to the currently ongoing projects. And throughout that research, I was able to study 60 spaceplane projects. The research phase review lasted for 4 years, and I was able to collect information from 172 reference sources and synthesize that information. So the overall study process, the first step was to collect the information from the spaceplane historiography, collecting all the information in terms of books, in forms of technical reports, in forms of the scientific publications in this area. And then going back into that massive pile of data, the next step was to understand what data exists and to categorize that in a structured format, where I was then looking at one particular individual spaceplane projects and putting together the data relevant to what they were looking for, what kind of goals were defined when the spaceplane program was going on. So that was the part of understanding of that data. And now based on that, I developed a mathematical process in which I could analyze and synthesize this data into some meaningful conclusions, and eventually being able to communicate the results, as we'll see ahead. So this is an example of, let's say, 5 or 6 spaceplane programs from the US in early 50s. And as you see on the right first, there are 5 blocks, 5 colored blocks, and each block refers to a design subsystem or design discipline. The very bottom one, the one in blue, actually means aerothermodynamics. And again, there are 4 other subsystems, including the structures and materials, propulsions, and other design disciplines that actually are analyzed to make a concept. And as you see on the right, on the left, you see different bars that shows how one individual spaceplane program was contributing. And some programs were contributing more in aerothermodynamics, but not so much in structures and materials, while some were doing the other way. They were looking for the innovation in structures and materials. So the idea behind this kind of study was to actually find which programs were contributing to which particular subsystems. And this shows the overall results for the US-based programs, where you can see how different programs were contributing differently to individual vehicles. And the same way for the European programs, where the first bit shows the programs initiated by Germany and the UK. And after the definition of ESA took over and conducted a lot of studies and programs into spaceplane developments. And this is sort of the overall results that show that. Another interesting result that came out of was how the designs evolved throughout these projects. This shows the history of evolution of design products, design concepts throughout the program in the US. And next we see the similar evolution in European programs. And this kind of understanding can help you connect the dots on a global scale, on a temporal scale as well, where you see the programs from 1933 to now, and you can make a connection of how one program influenced the other, what kind of technologies were passed on from one to other.
Yes, thank you, Loveneesh. If you would like to explain us a little bit more on the significance of these results now for us.
Sure. So some significance aspect that came out of this study was, first of all, the ability to capture knowledge from the history, and to be able to understand that knowledge, to identify what was done, what kind of innovation happened, and where does that innovation sits in what pockets of history, so that engineers who start today can actually go back and find out that information which is more relevant for them, instead of just randomly searching for that information. Another aspect that came out of this was the comparative assessment, that now we could assess different programs and find out which was more important than the others. Then there was this big picture influence by being able to draw these design maps that you could identify the influence of one generation over the other. And the last one being the approach of the modeling itself is very generic, and then we can apply that to any programs, be it satellites or be it rockets, and apply the same process and model the systems such that we can get the same kind of information and insights into different products.
Thank you. Yes, I see we have a last presentation.
Yeah. So this is the third application that I'm going to talk about on lunar exploration. And this was a part of a research accelerator program that I was involved in last summer. The program is conducted in collaboration with NASA, and FEDIL is the name of the program, while the Luxembourg Space Agency was the sponsor of this project. And the idea behind this project was to develop a high-definition maps of lunar poles. And why we were doing that was because we know that there is water on the moon. And the most likeliness of water existing on the moon is on the polar regions, in these so-called permanently shadowed regions. These are craters that do not receive sunlight. They have not received sunlight for millions of years, and some of the coldest regions on the moon. So there is a high likeliness that water exists in there. But because there is no light in there, so we cannot even look into there. And we don't know where exactly the water is. And that becomes a difficulty for us if we have to send a rover in the PSR, because we cannot see in the PSR. So we are not able to design the rovers because we don't know what path it's going to take and what difficulties it might face. This shows an example of how the images are captured by the Lunar Reconnaissance Orbiter, the spacecraft that is actually going around the moon for the last 10 years and is collecting information. And as you can see, that little circle, tiny circle in the middle is a giant crater on the lunar south pole. And the different strips you see are actually just one image that the Lunar Reconnaissance Orbiter takes in one go. So we have a lot of data, but the data is actually it's not pure, so to speak, in the sense that there is low light within the PSRs and high noise. So the resolution of images is not very good to plan a traverse into the PSR. And this is very similar to when we take a photograph from our iPhone in the low lighting conditions. It's very fuzzy. You do not see the exact same amount of details which you see if you take a photograph in the bright sunlight. And it's very similar to what's happening in the PSRs when the Lunar Reconnaissance Orbiter is taking the photographs of the darker regions. So the overall study process included collecting data that was in form of the images taken by the LRO spacecraft, and then being able to understand the data itself. Each image has several properties around it, and also the fact that with this understanding we were able to understand the nature of the noise. And based around that information, Our team developed the Horus, or the software which use the data and develop the machine learning algorithms to understand the noise and remove the noise in two-step process. And with that, we were able to generate a better quality images from the existing imagery. This is an example of one of the images that we are denoising. So as you see the lunar south pole, there are a lot of craters and a lot of these PSR regions. One of them is Wapowski crater, and we go into, as you see, the difference between the dark and the bright side. And within the PSR itself, the dark region is, of course, does not have as much light, but when we light up the region, you can see that if you go into detail, you see a lot of noise. And these results are now showing that how we, in a two-step process, we're using the machine learning algorithms to clear up the noise and improve the quality of the images, as you can see between the distinction between the original and the denoised elements. So with this type of application, you see the use of data into developing these new age machine learning and AI capabilities that can actually give meaning to the existing data. And some of the applications of this work could be in improving the accuracy of crater counting, in understanding the geology of the moon, in being able to eventually traverse, plan the traverses into the moon for the next generation of rovers, similar to what we sent on Mars recently. There is a lot of lunar excavations planned within the PSRs, and in knowing these images in a higher detail would help us to plan the traverses more accurately.
Thank you, Loveneesh. Could you also explain us, just before we end, a little bit, this is very interesting technology and research, but how can it be also applied to other fields?
So this actually is been going on for a very long time, that most of the applications that are developed for the space industry are translated eventually to domains beyond space technology. And data is just a new age technology that we are dealing with and developing technologies and algorithms and softwares around it. But this has been going on for a very long time. Scotch tape was developed to be used in the space. Similarly, there have been numerous applications that initially are developed because space provides this very rigid boundary conditions for which we have to come up with innovative solutions. But eventually, over the time, those technologies are migrated to the commercial industry, mm-hmm. and the same is happening now in form of the digital products that we are developing.
Mm-hmm. Thank you very much, Loveneesh. So if there are no further questions, I would like to really thank you for this very interesting presentation. This was very valuable for many of us, and I hope it also encouraged some of us to deep a little bit more into the space sector.
You're welcome.
Ladies and gentlemen, here we are at the end of day one of FEDIL Industry Days 2021. And it has been a very rich day. We had an interesting exchange with the Prime Minister and with our chairwoman, Michelle Detaille. We had an engaging discussion with the Commissioner for Jobs and Social Rights, with the Vice President of the Chamber of Commerce, Mrs. Valérie Massin, and with Madame Marina Andrieux, coordinator for the Digital Skills and Jobs Coalition. But we also got useful information, facts, evidence, and concrete examples on the subject of digital and STEM skills. This was an inspiring day, and I would like to thank each and every one of you behind the screens for your participation and for listening. Unfortunately, we were not able to reply to all of your questions, but we will try to do so as soon as possible via email. I would also like to thank our guest speakers who delighted us with very high-level debates and discussions of high relevance for the future of the European Union's digitalization. We at FEDIL would also like to thank our sponsors, Foyer Assurance and PGL BNP Paribas, again for supporting FEDIL Industry Days so generously. Not least, I would like to personally thank the team backstage and all the colleagues and friends who worked very tirelessly on this project to make it a success. We came here today to raise awareness on the economic and social impact of the COVID-19 crisis on Europe's digital future and on the need for a new industrial strategy nourished by talent. Don't miss tomorrow's sequences, where we will discuss a new industrial strategy driven by data and a new industrial strategy nourished by trust. Have a look at our program and you will see that we will entertain you with high-level presentations and debates. This is it from me. Have a lovely day and thank you. Bye-bye.